Hi, I'm Joseph Stankiewicz. I'm here today to talk to you about the O3DE Asset Pipeline. I'm going to start by explaining what asset processing is and why it needs to be done. Then I'm going to cover the asset pipeline for O3DE in particular, how the asset processor impacts working on an O3DE project. We're going to take a deeper dive into the asset processor and explore how it works, as well as take a visual tour of the tool. I'm going to explain how you work with assets in C++. And finally, I'm going to cover how you can bundle your assets, how you can take the content for your project and put it into a release build of your game project that you ship to your own customers. Asset processing is transforming content from a portable format to a runtime-friendly format. We call this converting source assets to product assets. As an example, you might have an image file, devtan.tiff, as you see, in the tagged image file format that the asset processor converts into two product assets, devtan tiff streaming image and devtan tiff 1002 image MIP chain. We do this because there's work we can do at tool time that optimizes the content for runtime use. This image file, devtan.tiff, is very portable. A lot of tools, Photoshop, Paint, can load this file and render it. However, it's not really optimized for being able to quickly be rendered on 3D geometry by a game engine, which is where the asset processor comes in, and it can take that information and process it for that purpose, as well as there's other information we can generate at that point, like a mipmap chain, which is useful to help manage graphical memory usage at runtime by providing a lower resolution version of the same texture. This isn't just used for image files. It's also used for things like scene files, 3D scene files, FBX files that'll spit out meshes and other geometry information useful for the runtime of a project. And other content types like XML will often have what we call a copy job, where the asset is copied as is from the source asset to the product asset. That way runtime code can make use of it. O3D's asset pipeline in particular starts with the asset processor. This is a tool that watches scan folders for unprocessed source assets. Scan folders are the place you put source assets to make them visible to the O3DE toolchain. Asset processor then sends information about these source assets to individual builders to be processed as jobs. When the job runs, the job then outputs a product asset, which the asset processor gathers information on and puts that in the asset database, asset catalog, and asset cache. When you launch the O3DE editor, one of the first things you'll notice is it launches the asset processor. When the editor is running, it's communicating with the asset processor because there's information that it can provide about assets and their state to tools like the editor. This is also true of the standalone PC launcher. When you launch that, by default, it's communicating with the asset processor. The other thing you'll notice when you launch the editor for the first time is it waits on critical assets to get processed first. This is content that's required by the engine. It's often things like shaders. If the shader's not processed, the engine can't render anything, so the asset is marked as critical. That way the asset processor, 1, knows to process it early, and 2, the editor knows not to load until the critical asset has been processed. This is a flag that's set by engineers who work in an individual asset builder to mark that asset as critical. That way the asset processor will know to treat it as critical when it sees the job is created. Another useful feature of the asset processor is job escalation. When you launch the editor, critical assets finish processing, you may have a lot of other assets that need to get processed before your entire project has been processed. In that case, if you go and start interacting with the editor, you load up a scene to work out of. Any content you start using, if it's in the queue and has not been processed yet, will get moved forward in the queue when it's referenced. That way the content you're using is processed sooner than the content you're not using. One of the important steps with working in an engine and on a project is going to be iteration. Very rarely is the first version of a file going to be the best on the one you want to ship with. So chances are you're going to want to make changes to your source assets and see those changes. The first step here is reprocessing. So when you make a change to the source asset, the asset processor has tracked the timestamp of when it last processed that file. If the timestamp on the file on disk no longer matches the timestamp of the last process, it will reprocess the file and you'll get updated product assets. There's also a concept of dependencies with assets. In this case, there are job dependencies and source dependencies that can impact an asset reprocessing. If either of those changes occur, if a job dependency, for example, updates. So an example of this would be a material file has a job dependency on a shader that it references. So if the shader reprocesses, that shader job runs again, the material will see that, and the material itself will reprocess in response to that because it might need more information from the output of the shader job. Finally, if the builder itself changes, if somebody changes the logic of how a particular kind of asset is processed, then every asset built with that builder will get processed. And this is handled through a concept called the builder fingerprint. When a job is run, the fingerprint for that job that was used with the builder is tracked. That way, if the builder's fingerprint no longer matches that job fingerprint, the job will get regenerated and the source asset will be reprocessed. The other half of this is hot reloading. You probably don't want to have to close down the editor to see a change to your product assets. If you're working on, say, that dev-tan TIFF we were looking at earlier, you want to make some changes to the image. When you change the source asset, the asset processor sees that, it reprocesses it. The streaming asset product asset is updated, and then the asset processor sends a message to the editor. And in the editor, the asset manager sends a message to any game logic listening for it that the product asset has been updated and it should be reloaded. This means that this is implemented per feature. So if you go and write your own component that references an asset, you'll want to make sure you respond to the message of an asset reloading, which we'll cover later. But the end effect of this is you have asset hot reloading. You see the product asset change in the editor in response to the change you've made to the source asset. That way you can iterate quickly, make changes, and see those changes updated. Files, source assets, are tracked by the asset processor in what we call scan folders. These are folders that the asset processor scans for content. Scan folders can contain more than source assets, but generally you'll want to, this is the only place source assets can be. If you put a file in a scan folder that the asset processor doesn't know how to process, it'll be invisible to the asset processor, which can be okay. Like you might have some documentation, maybe license information for a file you found that you acquired from an asset store. That'll help you track to make sure that you are legally using the asset like you can, but it isn't needed for runtime usage. It's just something you're using for development time. At that point, that file is not an asset because nothing processes it, nothing builds it. The asset processor keeps track of what it's processed by the timestamp, the file hash, and the builder fingerprint. So if the timestamp changes, the asset processor knows to reprocess the asset. The file hash is not used by default. The timestamp is a lot faster, but there's a fallback to use file hashes in cases where timestamps might not work for you. And finally, the builder fingerprint is set within the asset builder that processes that asset, and it's set by an engineer who worked on that builder. This can be anything that makes sense there. A lot of times this is going to be as simple as a version number. You'll have a number when you make a change to the builder. You'll want to bump that version number up, and then every asset built by that builder will get reprocessed. In other cases, like if you look at the scene builder that processes 3D content like FBX files, it is a collection of version numbers from different components. That way, if you change part of the logic for how 3D scene files are processed, the fingerprint will change, which means 3D scene files will all get rebuilt in response to that fingerprint change. Product assets are then what are created by the builder, and they're what you use at runtime and at edit time in the editor. When you load up the editor and you, say, place an entity in a scene, that entity has an asset reference. That asset reference is pointed at a product asset. These exist in the asset cache, which is a subfolder of your game project. You should not add these to source control because they are generated as part of this pipeline. You could have some unexpected thrash with putting them in source control, and it can be difficult to manage. You'll find yourself needing to add these constantly, as well as you might have some timestamp issues involved with different members of your team making use of product assets in source control. You can just rely on the asset processor to generate these product assets for you. You also shouldn't edit them directly for that reason, because if the asset processor reprocesses the source asset, it'll overwrite any changes and modifications you made to the product asset. If you do find yourself in a situation where you want to make a change like that, we recommend finding a way to make that change to the source asset. If it's a piece of content you can't change directly, like an FBX file is often output from a digital content creation tool like Blender, Max, or Maya. And if you edit the FBX file directly, that change won't be reflected upstream in the original file it was made. So either you can follow that to the root and make the change in the Blender, Max, or Maya scene, or you can make use of what we call sidecar files. You'll notice FBX files can have a file called an asset info file listed next to them that contains information on how to process that asset into the product asset. And that would be another place that you could put that data that you want to add, that you want to make changes to. But you shouldn't ever edit the product asset itself. The next part to know about this is when an asset is processed, it's processed for a particular platform. So if you're working on a game and you're targeting Android, iOS, and PC, you're going to have each asset processed for each of those platforms, which is done because a lot of times there will be different configuration per platform. Earlier, when we looked at that dev-tan TIFF that turned into the streaming image and the mipmap, oftentimes you're going to have different mipmap generation settings per platform. That way you can balance install size of your application versus runtime memory usage. And on a platform like PC, your customers will likely have more storage space available for the game, so you'll want to manage your runtime and graphics memory usage more than on a platform like Android and iOS, where storage space for the installed application will be much tighter, and you may instead prefer to take the trade-off of having less mipmaps, and so that way your install size can be smaller. The platform you're developing on, we call the host platform. So by default, this is going to be a platform like PC. And then the platforms you're targeting for release are your deployment platforms. There are cases where these might be the same. If you're building a PC game on PC, then your host and deployment platform are both PC. In other cases, it might be different. If you're building an Android-only game on PC, then you're still going to process assets for your host platform, because when you're in the editor making use of that content, you're going to want the content processed so you can use it in the editor, but you'll also process for your deployment platform, Android. Although depending on how your team's set up, you may have content creators who don't need to deploy to target. You might have an artist who is not testing on Android because they can get all their testing done on PC, and they may choose not to process assets for Android to save themselves time, and they only process for the host platform so they can quickly iterate. Source assets are identified internally by what we call a universally unique identifier, a UUID. You'll also see GUID, globally unique identifier. These are interchangeable. This value is generated based on the file name and the relative path to the scan folder it lives in, and it'll be the same on each machine for your project for that reason, because you want to make sure that if I am working with you on a project, that dev-tan TIFF image, if I reference it by the UUID, it should resolve to the exact same image on your machine as on my machine. The next piece of asset identification is with the product asset, which is a combination of the UUID for the source asset the product was created from, as well as a sub-ID, which is a value, a number that is tracked for the product asset, generated from the asset builder that processed the asset. The UUID in this case is the same as the source asset, but the sub-ID needs to be deterministic and unique, because these are going to be referenced by other things, like entities with a component will reference a product asset. So using the streaming image as an example, if I have an entity in my scene that references an image and it references a streaming image, it's not tracking that reference internally by the relative path to the image. It tracks it by this asset ID. So if the product asset changes, if the sub ID for that streaming image ends up different for the source asset, then my entity will end up pointing at a different asset than it was originally created with. These need to be unique for that same reason, because they are references. This is pretty straightforward when you only have one builder operating on a source asset, but there can be cases where there are more than one builder that use this same source assets as input. An example could be a height map builder that uses image files to generate height map for 3D geometry. These image files are the same image format, like .tiff, that are processed by the image builder that we saw that created the streaming image. So if you were building that height map builder, you would want to make sure that you did not generate sub-IDs that conflicted with the other builder, the image builder, that was generating product assets. If you make a mistake and there is a collision, the asset processor will let you know that there's already a product asset with ID, so it's pretty quick to resolve. Now we're going to take a deeper dive into how the asset processor does this, how it converts source assets to product assets. We're going to start with file scanning and go into details about those scan folders. Then we're going to look at asset builders, the code that does the work of converting source assets to product assets, starting with the job creation and then the job processing. We're going to look at the product assets themselves, and we're going to talk about the three kinds of dependencies for assets: source, job, and product. And finally, we're going to look at the output, where all this information goes: the asset database, asset catalog, and asset cache. File scanning is where the asset processor looks through those scan folders we talked about earlier. Scan folders generally are going to be one of three locations. Your project is a scan folder. It's a place you will put those source assets for your project. Any gems you have enabled. A gem is a modular collection of code and or assets. So it's something that you can turn on and off easily, and it can support assets, in this case, for your project, but you can also support, say, the entire builder and pipeline for a content, including the code that loads it. So you can have an end-to-end gem that has sample assets that demonstrate a new source asset. That gem could also have the builder that processes that source into a product, and then the runtime code that loads and uses the product assets. You can turn on that gem, you get access to all of that, or you can turn it off for your project and you no longer have access to it. The last place that source assets live by default are going to be the engine and editor folders, which is content that O3DE itself needs to run. So things like the default shaders used by the engine. These asset builders are a bundle of code the asset processor uses to build assets. And they have three steps here. The first is the descriptor, which is a quick way for the asset processor to filter source assets into an appropriate builder. Then job creation, which is where the builder will add jobs to the queue to be run. And then process job, which is when that job actually gets run by the builder. So the builder descriptor, there's additional information besides this, but in this case, these are the two things you need to know. The builder descriptor has a file pattern or file patterns it has registered with of asset types it cares about. So the image builder that turns that devtan TIFF into the devtan streaming image is registered with star.tiff, star.png, star.jpg, other file formats it can convert. The asset processor can use this as a quick way to filter content. That way it doesn't have to call additional code when it's scanning through those scan folders for what is an asset and what is just a file in a scan folder. The build descriptor is also where that fingerprint for the builder lives, and the version, one of the ways that you can use to trigger all assets to rebuild. If you modify the builder, you should modify the fingerprint, which will trigger all your source assets using that builder to rebuild. So after the asset processor crawls through the job descriptor to builder descriptor to match up each builder to an asset type, it then calls create job for each of those source assets. And create jobs is given a create jobs request, which has information on that file, the source asset to be processed. So in the image example, it would have information on that TIFF, a path to that file on disk. And then it's the builder's responsibility to populate a create jobs response with information necessary to process that asset, so that way the asset processor can create the job from that. So this is going to be a job descriptor. The builder will say, yes, I process devtan.tiff, create a job for that. And other information like a source and job dependency. So an example of a job dependency would be a material job cannot be run until the shader in the material referenced is processed. So there is a job dependency the material has on a shader to get processed. The create jobs response is where that would get populated. So in some cases, the create jobs response is pretty straightforward. You just look at the file, you add it to the job descriptor, and you're done. In other cases, you're populating these dependencies, or you may even do a little bit of cracking open the file to take a look at the contents to see if it's in a format you care about. So the example earlier with the image file and having a second builder that processes height maps, maybe you examine the file to see if it's grayscale before you decide if it's a height map or not, because you don't want to process images that are not grayscale as height maps. You could do that in create jobs, but oftentimes you might want to do that in process jobs as an early out, because process jobs are run multi-threaded, while create jobs is a single-threaded process right now. After all those jobs have been created, the asset processor has run all source assets through that create jobs call. Then the jobs are run in parallel on multiple asset builder executables in memory, where the process jobs is called for each individual builder on that job request, which was created from that create jobs response. So the asset builder process jobs has a process job request it gets as input, and then it populates the process job response with information on the product asset it created, as well as sub-IDs and product dependencies. The process jobs function will create the product asset on disk in a temp folder. That way the asset processor can take care of moving that to the cache. And it'll put information to help the asset processor track and find that asset, as well as the sub ID for it. Source and job dependencies are entirely a process time concept. A source dependency is a marker that whenever a source asset changes, this job should rerun. You'll use this in cases where effectively you will have more than one source asset that might feed into the same job. An example of this is with scene files, with FBX files. You can have a sidecar file, a .assetInfo, that has rules on how to process that file. You can mark that assetInfo file as a source dependency, and then when that assetInfo file changes, the FBX will get rerun through the scene processing job. Job dependencies are where you need to make use of the product of another job before you can run the current job. This is where the materials and shaders come in. A material needs to know information about a shader product asset to be able to process the material, so the material emits that as a job dependency. This supports optional and required. So if you have a case where if a file is available, you'll make use of it. But if it's not available, you can still safely process. You can emit that as an optional dependency. Otherwise, you can mark it as required, and then your job will fail if that dependency doesn't exist. While source and job dependencies were entirely a tool and processing time concept, product dependencies are entirely a runtime concept. They're not used during asset processing. They are data the asset processor has that are generated from the process jobs function on the relationship between these product assets. They are used in two areas. One is runtime loading. When you go to load content, oftentimes you want to have any product dependencies of that content also loaded and available. That way you can just have everything ready to go at once. Or asset bundling. When you go to take all of the content for your project, you want to put it all in a package together. You want to think about it at the highest level concept possible. You want to think about it like, I'm going to package up my project with the level 1.prefab. That by making use of these product dependencies and the graph that it builds, that'll pull in everything that level 1.prefab references and everything they reference via that graph. This also supports optional and required dependencies. So if you have a case where you will make use of a product asset if it's also available, you can mark that as optional. If you need that piece of content there, you can mark it as required. That way, when it's not there, these other steps in the pipeline will fail. The asset bundling can fail because the product dependency is missing. All of this information is initially stored in the asset database, which is what the asset processor uses to track what work it's done in the past. This is how the asset processor can also help resume when you shut it down in the middle of processing and relaunch it. It knows everything it's done because it's writing that to the asset database as it completes it. This is development time only. It's not used by the editor, and it's not used by a final runtime game you ship to your customers. And it's not just information about assets, it's information about the scan folders it's found and it's using, the builders, the jobs that it runs. That way it can keep track of that when it goes to generate the other information, like while it's creating jobs and processing jobs, that'll be important for it to actually generate those jobs. The asset catalog, though, is the runtime place this information is stored. It's generated by the asset processor. The information is in a lot of ways a stripped down version of the asset database. It's just what the runtime uses. So when you're interacting with code to load and manage assets, you're writing code that talks to the asset manager. The asset manager is then using the asset catalog to help find the content on disk you're requesting and deliver that to your code as an asset. The asset cache is where all of this lives. The product assets are put in the asset cache, which is a subfolder of your project, and the asset database and catalog are in the cache as well. So in the worst case, if you delete your asset cache, everything will get regenerated. You'll get back to ideally where you were before you deleted it. But this is a folder you'll often want to leave and keep around to save yourself time between running the asset processor and editor. That way it only has to reprocess what's changed since the last time you loaded and not reprocess everything if you delete the asset cache. Now we're going to take a walk through the asset processor itself. We're going to look at the tool. When you load the asset processor, the first thing you'll notice in the top left is the status, which will tell you how many jobs have been created, how many have been processed, if it's doing work. In this case, because I've already processed everything, I just have an idle state. Under that, you'll see what project and engine you're working out of, which is especially useful if you have multiple projects or engines on your machine. It can be a quick way to verify you're working on the project you intend to work out of. And then the port it's communicating with other processes on. We see at the top right some performance metrics about scan time, job analysis time, and job processing time. These can be useful to keep track of and see where you're spending time in your asset processing. You'll see here I did 0 processing because I hadn't modified any content since I last relaunched the asset processor. So it spent about 1.5 seconds scanning and then about 2 seconds analyzing any jobs it might have to run. We have a help button you can click here to bring you to documentation about this tool. And then on the left, you'll see a series of buttons that switch between tabs for the asset processor. We'll start with the Job tab, which shows information about the jobs that we just talked about, those jobs that are taking care of converting the source assets to product assets. Jobs can have several states. The initial state they start in is pending, which means the job has been created, but it hasn't been run yet. Then, once the asset processor starts running the job, it'll move to in progress. And finally, there are 3 completion states. In this case, you see these jobs completed without errors or warnings. So if we look at that dev-tan TIFF image that we used as a sample earlier, we see it processed here. It ran with the TIFF Atom compiled job key on platform PC and completed a couple weeks ago. Assets can also complete in 2 other states, completed with warnings and errors or failed. An asset failure happens when the builder just couldn't process that source asset into a product asset at all. The most common case you'll see of failure is if the builder crashes. If there's some internal logic to the builder that failed, and the builder crashes, like maybe there's a null pointer check that's missing, the asset processor, because it loads these builders as separate executables, the asset processor won't crash when the builder crashes, and instead the asset processor will catch that and mark that as a failed job. Every time you launch the asset processor, it reruns all failed jobs. Hopefully the asset will be ready to be reprocessed, because if you have something that is an asset that isn't processing, you actually probably want a product asset to use. The other 2 completion states are completed with warnings or completed with errors. And you'll see here you can have both, like this file completed with some warnings and some errors, ocean component level.pack. This is something that's decided within the internal logic to the builder. So when somebody wrote this scene compilation builder, for example, that compiled this physics dev sedan, they emitted a warning based on the content they saw in there. We look at the warning here. We see that it's because the asset was told to use source scene tangents, but those aren't available. So instead it defaulted to using mict for tangent generation. In this case, this is a warning because the intention of processing the content didn't match the result, but the product asset could be generated and it will still be usable. It still has tangents. It still can be rendered and made use of at runtime. An asset error, though, is generally going to be something that couldn't be processed in that way. Something was encountered and information got lost in processing. In this case, you'll see that this ocean level has a invalid element within the serialization. So there was something in there, a class that was removed that is no longer available. And so this ocean level will no longer function the same as it would have functioned when originally authored, because that logic, the serialized class, is no longer available. The decision between warning and error comes down to the engineer who is working on the builder. And the guidance I just walked through, warnings when it's something you can provide a useful fallback for and output what feels like a complete product asset. Errors when there's data and information missing, but you can provide a partial product asset. And failure when you just cannot generate a product at all. Those are the 3 ways we recommend you think about emitting errors, warnings, and failures. The next tab is the Assets tab. This is where you can view the actual source and product assets of your scene or of your project. You'll see what looks like a file tree that might match what's on disk. The important thing to note here, though, is this is a view into the asset database and not the files on disk. So if you have content in these folders that is not an asset, then it won't show up here because this is only showing what the asset processor has processed. If we select that dev-tan image we've been using as a sample, we'll see the information here about it, the scan folder it lives in, the source UUID for that devtan image, as well as the two product assets we looked at earlier, the streaming image and the bitmap chain, an optional source dependency that is not satisfied because there's no button to jump to that source dependency, and finally two incoming source dependencies, other assets that require this to be built before they can be processed. There is a right-click menu that doesn't show up here because the capture settings that lets you view the job that ran on this, any product assets, open in Explorer, copy the full process, copy the full path to the asset, or reprocess the asset if you need to regenerate the product assets. We can click on this little button here, the Go To button, to jump to the product asset on the product asset tab, where we see the other information about it, the product asset ID, which is that source UUID combined with a sub ID of 1000, the time it was processed and the job key it was processed with, the platform it was processed for, a link back to the source asset, as well as that product dependency on the bitmap chain. So that way, if you go to package or load the streaming image, it'll pull in this associated bitmap chain as well. Next, we have the logs tab. Note that these are logs for the asset processor itself and not logs for jobs. Most of the time, when you're trying to debug a job that is not behaved like you expected, you'll want to start with the logs for that job, like we see here. If the asset processor itself is having problems, then that is where you'll want to come here and try to debug and find information. Like we see here, there was an issue where it couldn't find a log for a job, so that would help verify if that log was missing. I would see the error message here and know that I had since deleted that log. The next tab is the Shaders tab. This is for our legacy renderer. It's not in use by the Atom renderer. The Connections tab shows the asset processor and how it's connected to different tools. You'll see here we're only connected to an asset builder. Those are those separate executables that connect to the asset processor and do the work of processing the content. This means that if the builder crashes, the asset processor won't crash. Instead, it'll just notice the builder is no longer available and mark that job as a failure. If I was running the editor, we would see that connection here. And if I wanted to have an Android device or an iOS device as an example connected that I was using assets served from the asset processor, I could use this tool to add that connection as well. Finally, we have the Tools tab, which is what you can use to debug a couple workflow issues. We have faster scanning mode on by default, which is where we use the timestamp on source assets to know if the asset's been modified. Almost all of the time, you're going to want to use this because it's much faster to check a timestamp than it is to hash the entire file and compare the hash. The area that you might find that you're using this is if, for example, you are putting all your source assets into a zip file and then pulling them out of the zip file format actually truncates timestamp, and so you'll end up with a different timestamp than you expected. Or if you have some source control settings that aren't as standard and you have source control writing file times in a way that results in files having their timestamps go back in time or not update as expected, then you might need to turn faster scanning mode off. But we would recommend reconfiguring your source control settings in that case because faster scanning mode is faster. Performing a full scan can be useful if you've made changes to the asset cache, either intentionally or unintentionally. If you don't want to delete the whole cache and recreate it, but you're okay spending a little bit of time having the asset processor rescan and make sure it has no work to do, then you can use this button to start that scan. Now I'm going to talk about working with assets in C++. When you are writing logic, which will usually be a component, you're going to want to start with an azData asset of the asset type you're working with. If you're using content that already exists, like if you're using a streaming image, there will be a streaming image asset type you can use here. If you're building a new asset type, then you'll write that here, and you'll want to match the product asset when you build an asset type. This is important to remember because a lot of the time a single source asset will have multiple products. Like we see with the image, it has a streaming image and a bitmap chain. From there, you'll want to connect to the asset bus for that asset's ID because a lot of this functionality is asynchronous. We recommend using qload to load assets in the background. If you need immediate access to the content and you want to do a blocking load, you can. But one of the reasons to use qload is you're probably going to want to build your component to be able to handle content not yet available and content reloading. That way your content creators can work fast in the editor. Earlier when I talked about hot reloading, this is where you hook this up for any logic you're writing, one of the messages the asset manager will send to your logic, if you want to hear about it for an asset, is the onAssetReloaded callback. That is the message that's sent when a product asset's regenerated, when something that already exists is changed and updated. You can listen for that message, and then you can drop any information that you have pulled from the previous product asset, and then change your references to point at this newly reloaded product asset. This means that things won't get pulled out from under you as well, so you won't have a case where you have a pointer go bad if you are still using the old product asset for some reason. If you want an example of this, I recommend looking at the editor collider component and the collider component. They're a good workflow there to see how asset management is handled, in this case for geometry used as collision information in the editor and runtime. When you're thinking through adding a new asset type to O3DE, you're going to want to think about what that source asset is and what it looks like. In some cases, this is going to be the O3DE editor itself. You'll use the starting point for editing and creating an asset. If you look at the material editor or prefab system, these are examples of that. The prefab system creates a prefab file in your project, so you load the editor, you create a prefab in the editor. That source asset is the source of truth for that content as well. In other cases, like with the TIFF we looked at earlier, devtan.tiff, chances are this is actually an intermediate asset, and the source of truth is upstream in something like a Photoshop document file. That image is probably exported from Photoshop, and so in that case, that workflow is going to be a little different. When you're adding new content, a new asset type to O3DE, you want to think about that when you build out that pipeline, how that source asset gets in and how it gets generated. In some cases, you can and will want to create that source asset within an editor in the O3DE editor. In other cases, it's going to be a step in a pipeline like I just covered with images, as well as like an FBX is output from a Blender scene or a Maya ASCII file. If you're building an in-editor tool, you should edit the source asset and not the product asset, because the product asset is downstream of that source asset. You may have a case where your source asset and product assets are identical, and that's okay. You can just make a builder that is a copy job that copies the source to the cache as a product, but you'll still want to edit in the source folder. That way your content creators can safely put that content in source control. You want to load your source asset outside of the asset system if possible. Well, entirely, because the asset system is mostly used for managing the product asset. So you'll see in a lot of these tools, like the material editor, they are using other functionality to load the source asset that you are editing. One of the easiest ways to do this is because you're probably building that tool using Qt widgets. You can use Qt's file system to also load the file, and that way you can edit it, save the file to the source asset, and then your builder you write for your source asset will pick that up in the asset processor, create the product asset, and then when you go to load that content in edit time or runtime, so if you then build a component that's on an entity in a scene, that's where you use the product asset and the asset system we covered in the previous slide. The final step we're going to cover is asset bundling, taking all of this content and getting it to a release build of your project. A release build is what you are going to ship to your customers. The build you're working with day to day, the editor connected to the asset processor, that's a lot of information that you don't want to ship to your customer for a lot of reasons. The simplest one is going to be file size. Part of creating the release build is going to be packaging up the content for your project. And when you're doing that, you're going to want to package up only the content you're using and only the content that you want to ship. This is because download and install size can be very important for a lot of your customers, especially on mobile devices. You might have some secrets and content that shouldn't be released yet. So if you're getting near the end of your project, and if your project's a game, you may have a content creator who's already working on expansion content because they've finished their duties for the core release of the game. But you don't want that expansion content to get leaked early. You don't want the players to spoil the fun for themselves when they go and open the file folder on disk to look for secrets. You don't want them to find out who, say, the boss of the expansion is. Instead, you want them to discover that when the expansion, like at the proper time, when you release the expansion, you don't want them to spoil their own fun. So you can use the asset bundler to help manage that secret content. And finally, you'll want to manage the patching and patch sizes. Very similar to the download and install size. the size of a project and the size of a patch can be important to your customers. They don't want to, and you don't want to have them re-download the entire project each time you have a release. Ideally, they only have to download what's changed since your last release. This is managed through the Asset Bundler, and it's one of the core reasons the Asset Bundler was built the way it was built, was to help you manage your patches and keep the patch size down. So the Asset Bundler starts with either a graphical or a command line tool. We recommend using the graphical interface as a way to learn the tool, and then move on to the command line interface once you have a repeatable process you want to apply and potentially run on an automated build machine. You start with a list of asset seeds, which then you expand into an asset list based on their product dependencies. You can manage those asset lists with rules. That's where patching comes in. You can run a rule that will strip out content that has only been changed since your last release. That way you can package up only the new content. Then you generate a bundle from the asset list, and that bundle is a pack file that you put into your release build of your project. Asset seeds are the highest level concept of what goes into your game. Chances are nobody in your team is going to know exactly what product assets are used everywhere in your project. Let's say you're working on a racing game and you have 10 tracks you want to ship, and then you have 5 tracks, test tracks, sample tracks, and expansion tracks that aren't going into the base game. If somebody comes to you and says, are we using devtan.streamingimage in the base game or the expansion, you might not know, and you don't want to have to go load all 10 tracks to see if that's true. Instead, with the asset seed system, you can think about your project and your bundles at that high-level concept of just those root prefabs, or levels. So you go to create your asset seed list for your game. You'll have, say, these 10 tracks as 10 different seeds. And when you go to create the asset list from those seeds, the asset bundler will crawl through each product dependency recursively, so it'll see those relationships. So it'll find that devtan if, for example, it was on a bench in a level, then your track1.prefab will point to bench.prefab, which will point to devtan.streamingimage, and that image gets pulled into the asset list because it was on the dependency graph. When you're processing and building your asset seeds, you can mark them with multiple platforms. And you'll want to track these in source control. This is so that way you can generate patches later. An asset list file is that expanded list of product assets from the asset seed file, or by managing other asset list files using asset list comparisons. These contain the modification time of a product asset and file hash, which are used with the asset list comparison feature to help you generate that patched content, the change between the last release and this release. At this point, this becomes platform specific because these bundled asset bundles are going to be platform specific. What the content you bundle up for Android is going to be different and bundled up differently than how you create your release build for your Windows project, for example. You'll want to track these in source control as well. That way you can generate patches later. You likely, if you're generating a patch a month after your initial release, you don't have a complete copy of your project when you did the initial release. But if you have that asset list file that has the file modification times and file hashes for content, then the asset bundler can help you generate that difference and create just the patched content. Finally, you use the asset bundler to generate these asset bundles from the asset list files, which is that packaged content of product assets for use by the runtime of your game. So let's take a look at the asset bundler itself. When you load up this tool, you'll see at the top here, we have a list of tabs that match that workflow: seeds to asset list to rules, back to asset list, and finally to completed bundles. I've created an asset seed list of that devtan streaming image here, which you'll see has the PC platform. Then I created an asset list from that, which added the mipmap chain, which matches that workflow and expanded it to the product asset. I could run a rule. In this case, I have a rule that would just add streaming images, but I'm not going to. Then I can generate a bundle from this asset list, which gives me this completed asset bundle that I would put in the release build of my game project. So now we've covered what asset processing is and why it needs to be done, how the O3DE asset pipeline works. We covered how the asset processor converts source assets to product assets, and we took a visual tour of the asset processor. Then we covered working with assets in C++, and finally bundling content for the runtime of your game project. If you have any questions, you can reach out on the O3DE Discord or the O3DE GitHub discussion page. Thanks for watching.